Section 2-4, continuity and discontinuity. This is part 2 of section 2-4 for us. Let me remind you of the objective of this section. Given a function, determine points of continuity and discontinuity, and find one-sided limits. And in particular, we're going to look at one example here, example 2. And this is going to be a question about making a function continuous, or determining key values in order to make it continuous. So example 2 says, let h of x be the following piecewise function. Let's go ahead and write this function down. H of x is defined as the piecewise function kx squared is the first piece, and that's if x is less than 2. And the other piece is the absolute value of x minus 3 plus 4, and that's if x is greater than or equal to 2. So we have ourselves a piecewise function there. Now for part A, it says to find the value of k that makes the function continuous at x equals 2. You'll notice that x equals 2 is the key value there in the domain of this function where it switches from one piece to the other. So we want to do what we can to make it continuous there. I know that the first piece of this function is a quadratic function. I know that's continuous everywhere. The second piece is an absolute value function, and that's continuous everywhere. So the individual pieces I know are continuous everywhere. It's where they switch over from the first piece to the second piece at x equals 2 that we're concerned about. So for part A, we want to determine if this thing, well, I shouldn't say determine if this thing is continuous. We want to force it to be continuous is really what we're trying to do. Find the value of k right here. That's going to be the right value of k to make this thing continuous. All right. So going back to our definition of continuity. Remember the definition of continuity? There's 3 parts to it. The first part is, does h of 2, in this case is our function, h of 2 exist? That's the first question we've got to answer, and of course I want the answer here to be yes. And if it's an answer if I don't know right now, then I've got to do what I can to force that to be yes. But you can go up here to the definition, and I can see that if I plug in 2, that's the second piece of this piecewise function. That's the absolute value part. So I can actually evaluate that out and see what we end up with. H of 2 is equal to, it's the absolute value of 2 minus 3 plus 4. And the absolute value of 2 minus 3, that's of course a negative 1, so the absolute value of it's a positive 1, plus 4 would give you 5. So the answer here is yes, it does exist. Now even if this was the piece that involved the k, I could still determine that this thing exists because k is going to be some number. So even if the answer ended up being 5 times k or 5 plus k, k is some number, and I know I can multiply, I can add values to k, I can subtract values from k, and so forth. And in fact, I can divide by k as long as k is not 0. So even if this has been the piece with k, I would find out that this is always going to be true. And for that reason, I'm showing you this 3-step definition here that we've got to go through and make sure each of the pieces of this definition are met. But we don't need to check this every time because we know that this part's going to be met. The second part of the definition of continuity deals with the limit. So the question is, does the limit as x approaches 2 of h of x exist? And because this is defined as a piecewise function, and the 2 pieces, or we switch from one piece to the other at this key value of x equals 2, this is really the part of the definition that I got to make sure that I meet this part. This is really what it's going to come down to. So I have to force, if I go back up to my function h of x here, I have to force the limit to exist at x equals 2. Well, if you go back to our one-sided limits, we said that with one-sided limits, the only way that you know that your limit exists is if the limit from the left side and the right side are the same, then my limit exists. So that's really what it's going to come down to here. I need to force the limit from the left side to be equal to the limit from the right side. So I'm going to take the limit as x goes to 2 from the left side of h of x, and I have to force that to be equal to the limit as x goes to 2 from the right side of h of x. All right, so let's replace h of x with what it's equal to here. Now it depends on what piece we're dealing with here, obviously, as to what function we're going to fill in there. So if we're approaching 2 from the left side, going back up to our function, approaching 2 from the left side, that's values of x less than 2, so that's the kx squared part. So this is kx squared. And I need to force that to be equal to the limit as x goes to 2 from the right side of h of x. And again, h of x now, as we're coming into 2 from the right side, is the other piece. That's the absolute value portion of this. So it's the absolute value of x minus 3 plus 4. So I have two limits basically that I'm trying to force to be equal to each other. And really the only unknown that I'm going to have here is the k. So I'm going to be able to solve for that. So again, to evaluate a limit, what we've learned is the first thing you do is substitute in a value of x. So we're letting x go to 2 here on the left side. So it's going to be k times 2 squared. In fact, I'm going to go ahead and write it that way just so you see the substitution again. And on the right side, we're going to do the same thing. Replace x with 2. We're letting x go to 2 from the right side, but we replace it in this problem with the 2. So we have the absolute value of 2 minus 3 plus 4. And now let's just simplify this. So on the left side, we end up with 2 squared is 4 times k. And on the right side, again, you have the absolute value of 2 minus 3. That's a negative 1, but the absolute value of that makes it a positive 1. Plus 4 gives us 5. And so if we divide by 4 to solve for k, we end up with k is equal to 5/4, or that would be 1.25. And that's the second piece of this definition, that if now I can see that if I force k to be equal to 1.25, I'll have the limit from the left side being equal to the limit from the right side, and thus once that happens, I know that the limit exists. So this would end up being a yes. And again, this right here, as turns out, is the work that we need to show. I'm going to go ahead and put that in red here, that this right here is the work we're going to have to show for each one of these problems. And that's because of the fact that I have to force the limit from the right side and the left side to be the same. Okay? But I'm going to go ahead and put up the third step of this process, or third part of the definition of continuity, just so we remember what it is. And the third part was we have to figure out, does f of, oops, it's not function f, it's h here. Does h of 2 equal the limit as x goes to 2 of h of x? And so we've already found out what h of 2 is equal to. We've already found out that h of 2 is equal to 5. And we can go through and find what the limit from the left side and the right side of our function is, now that we've determined this value of k. But if we take the limit as x goes to 2 from the left side, that's the kx squared, so that's going to be the 1.25 x squared. Again, we said that k turns out to be 1.25. And if we plug in 2 squared is 4. 4 times 1.25 gives us 5. So the limit from the left side is 5. Take the limit as x goes to 2 from the right side. That's the absolute value function, the absolute value of x minus 3 plus 4. And again, if you replace the x there with 2, 2 minus 3, that's a negative 1. The absolute value of that is a positive 1 plus the 4 gives us 5. So this tells us that the limit as x goes to 2 of h of x is in fact equal to 5. So to answer our question here, the h of 2 is 5. The limit as x goes to 2 of h of x is also 5. So the answer here is yes. And again, that's going to fall into line every single time with these types of problems. So the first part of the definition, we don't have to worry about. The third part of the definition, down here, we don't have to worry about. It's this second part of the definition is what we've always got to come back to and determine, does the limit exist? And in fact, actually what we need to do is force the limit to exist by forcing the left-handed limit to be equal to the right-handed limit. All right, the last part of this one says to plot and sketch the graph. So I'm going to switch over to our calculator here. And they've given us a piecewise function. We've seen how to graph these pieces before, but in example 1 we saw that. So I'm going to just punch this in like we've done before. It's 1.2, oops, I go to y equals, it's 1.25x squared. Again, that's our value of k, substituted in. And we divide that by the domain of x less than 2. And for the other piece, now this has an absolute value function in it. And you actually have an absolute value function on your calculator. That's under your math menu. So if you go to math and go over to num, you'll find absolute value. And it's the absolute value of x minus 3 and then plus 4. And we're going to divide that by its domain, which was x greater than or equal to 2. And I'm going to just graph this. I'm going to start out in the standard window here just so that you can see what it looks like in the standard window. Again, you got to watch out because sometimes your calculator might have some difficulty sketching this. It didn't do too bad there for me. Sometimes it might show where it changes over at x equals 2. It might show a discontinuity, and definitely be cautious of that. Go back and make sure that your math is correct there, or double check your calculator, whatever the case may be. But if that happens, just realize that sometimes it's the difficulty the calculator's having, not necessarily anything that you've done wrong. All right, and that is the end of this section.